Nearly 15 billion miles from Earth, a spacecraft older than most people alive is listening to something no one expected to hear. Deep space is supposed to be silent, a vacuum, nothing. But Voyager is hearing a hum, a steady, electric whisper coming from every direction at once, and it is getting louder. You are about to travel to the edge of our solar bubble, through a cloud of ancient stardust, past an invisible wall made of magnetism, into a region where something fills every cubic inch of so-called empty space. If this blows your mind, hit subscribe and stay with us. Strap in. We begin. October 2012. 15 billion miles from Earth. A 40-year-old spacecraft is drifting into the dark at 38,000 miles per hour. Its cameras are off. Its heaters are dying one by one. Most of its instruments have been put to sleep to save power, but one instrument is still awake. Two thin antennas, each stretching 30 feet behind the spacecraft, are listening. They were never designed for this moment. They were built to study the magnetic storms around Jupiter and Saturn decades ago. Nobody on the original team expected them to still be working. Then, on a quiet day in late October, they pick up something. A tone, faint, rising slowly in pitch. It lasts for weeks. Back on Earth, at the Jet Propulsion Laboratory in California, engineers stare at the data coming in. The signal is 22 hours old by the time it reaches them. That is how long a radio wave takes to travel from Voyager to our planet at the speed of light. And what they are seeing does not match any model of empty space ever written, because empty space is not supposed to ring. For decades, scientists believed that once you left the sun's protective bubble, you entered a true vacuum, a place so barren that a single atom could drift for miles without touching another. The textbooks called it the interstellar medium, but the number 0 was close enough. Almost nothing, almost silence. Voyager just proved them wrong. The tone the spacecraft detected was the sound of electrons vibrating, not sound the way your ears hear it. Electromagnetic oscillations, translated later into audio that researchers could actually play through a speaker, and when they did, it sounded like wind through a long metal tube, a low moan, a hiss that rose and fell. Something was out there, something dense enough to ring. The physics is simple once you know what to look for. When a shock wave from a solar storm races outward from the sun and hits a region of charged particles, those particles start oscillating at a specific frequency. That frequency depends on how crowded the particles are. The more crowded the space, the higher the pitch. The emptier the space, the lower. Voyager heard a pitch that was far too high for empty space. Far too high by a factor of 20 or more. Whatever Voyager had just entered, it was more than 20 times denser than the region of space right behind it. Scientists had predicted a jump. They had not predicted this. Stella Ocker, a young researcher studying the data years later, would describe these moments as whistles. Brief, ghostly signals arriving once a year or so, each one a clue about the density of the medium. Voyager was now swimming through. Each whistle a fingerprint left by the galaxy itself. The team checked the numbers 3 times, then 4. Then they sat in silence in the conference room. Voyager had not just crossed a boundary. It had entered a different kind of space entirely, one that was alive with particles, one that was crowded by the standards of the cosmos, one that was humming. And the strangest part was still hidden in the data, because when they looked closer at the rising tone, they noticed something none of their models had predicted. The density was not steady, it was climbing. Voyager was moving deeper into something, and whatever it was getting thicker. For most of human history, the space between stars was imagined as pure nothing. Ancient astronomers pictured the stars as lanterns stitched to a black dome. Later thinkers imagined a cosmic ocean of ether, an invisible fluid through which light moved. Then, in the early 20th century, Einstein's work on relativity erased the ether. Experiments had already failed to detect it. Space, physicists decided, was simply empty, a clean, cold, featureless stage on which matter performed. And for a long time, that picture worked. Telescopes could see stars clearly across enormous distances. Light from a galaxy 10 million light-years away arrived at Earth with almost no distortion. If interstellar space were full of gas or dust, that light would be scattered, dimmed, reddened. Instead, it arrived crisp. The conclusion felt obvious. Between the stars, there was nothing worth mentioning. Then came the 1920s. A quiet Swiss-American astronomer named Robert Trumpler started noticing something strange about star clusters. The farther away a cluster sat, the dimmer its stars appeared, which made sense. But the dimming was happening faster than simple distance could explain. Some light was being absorbed along the way. Something invisible was standing between Earth and those distant stars. Dust, tiny grains, each smaller than a speck of smoke, drifting through the dark. Not a lot, but enough to matter over trillions of miles. The vacuum was not a vacuum. Over the following decades, evidence piled up. Radio telescopes detected hydrogen gas filling vast regions of the galaxy. Ultraviolet observations caught the fingerprints of atoms Earth's atmosphere would never let through. Astronomers began building maps of what they now called the interstellar medium. It had clouds, it had temperature, it had structure. Still, even with all this new data, the density numbers felt absurd. 1 atom per cubic centimeter, maybe less. In some regions, a single hydrogen atom floated alone in a volume larger than a coffee mug. Compared to Earth's air, which holds roughly 27 million trillion molecules in that same space, the difference was almost impossible to picture. Scientists had a joke. They called the best laboratory vacuums on Earth laughably crowded compared to the space between stars. So the old picture stuck, in a softer form. Yes, space had some stuff in it, but from a human point of view, it was close enough to nothing to call nothing. This is the belief Voyager was about to demolish. Because here is what the old picture missed. The interstellar medium is not just atoms drifting in the dark. It is a layered environment. It has hot regions, cold regions, magnetic fields weaving through it like threads, cosmic rays slicing across it at nearly the speed of light, plasma, that fourth state of matter where electrons rip free from their nuclei, filling huge volumes with a charged, humming soup. You cannot breathe it, you cannot see it with your eyes, but it is there, and it has weight, and it has pressure, and it pushes back against anything that enters it, including our sun. The idea that deep space was empty was less a discovery than a convenience, a simplification made when the tools to see deeper did not exist. Now those tools exist, and they are telling us something uncomfortable. The space between stars is full of something, and one small spacecraft, launched before the first personal computer was sold, was about to be the first machine from Earth to feel it directly. Picture a spacecraft the size of a small car. It is shaped like a golden satellite with a large dish antenna pointed permanently at Earth. On its body, protected by layers of foil, sits a nuclear power source the size of a large coffee can. Everything about it looks purposeful, compact, engineered for survival. Then you notice the antennas. 2 thin rods stick out from the back of the spacecraft. Each one is 30 feet long. They point in opposite directions, forming a wide V shape against the stars. On Earth, engineers nicknamed them the bunny ears. They were almost left off the mission. When Voyager was designed in the early 1970s, every ounce of weight on the spacecraft was argued over. Every instrument had to justify its place. The plasma wave subsystem, the instrument the bunny ears feed, was pitched as a way to study the magnetic environment around Jupiter, Saturn, Uranus, and Neptune. Planetary science, that was the mission. Nobody on the original team was planning for interstellar space. Nobody thought the spacecraft would still be alive that long. But they built the antennas anyway. 2 long rods of beryllium copper, lightweight, durable, designed to detect extremely faint electrical oscillations in the surrounding plasma. The thinking was simple. If you stretch out a big enough antenna, even the weakest signals become readable. How weak? Imagine trying to hear a single mosquito fly through a stadium during a rock concert. That is the order of sensitivity these antennas aim for. And for the first 35 years, they mostly did their intended job. They recorded the screams of Jupiter's magnetic field. They caught lightning on Saturn. They mapped the strange auroral signals of Uranus. By the time Voyager 1 passed Neptune in 1989, the instrument had done everything it was asked to do. Then the mission simply kept going. Year after year, the spacecraft drifted farther from the sun. The planets shrank behind it. The signal got weaker, but the antennas were still extended, still listening, still ready. Here is what makes them remarkable. In deep space, there is no air to carry sound. Your voice would not travel an inch out there. But charged particles, electrons and protons, floating in plasma, do vibrate. And when they vibrate, they create electric fields that move through space at the speed of light. The bunny ears feel those electric fields. A tiny voltage flickers across their length. A sensor inside the spacecraft records it. That signal gets beamed back to Earth, where engineers translate it into numbers, then into frequency plots, then sometimes into actual audio files you can play on a laptop. When NASA released those audio clips, people were unsettled. They sounded like wind in a cave, like a broken radio catching the ghost of a transmission, like something the universe was whispering that had never been meant for human ears. Every sound you hear from Voyager is real plasma, oscillating 15 billion miles away. The instrument has now outlived its original design by nearly 5 decades. Its team calls it one of the most successful scientific tools ever built, and its best discoveries were never the ones it was designed for. The bunny ears were built to study planets. They ended up mapping the shape of the cosmos itself, and in late 2012, they were about to feel something the team still cannot fully explain. 25th of August, 2012. Voyager 1 is 122 astronomical units from the Sun. That is roughly 11 billion miles. A single radio signal from the spacecraft now takes about 17 hours to reach Earth. On that day, something changes. The cosmic ray detector, another old instrument on board, shows a sudden spike. Particles from deep space, the kind that are normally deflected by our sun's magnetic field, start pouring in at much higher rates. At the same time, the particles coming from the sun itself drop almost to zero. It is as if a door has closed behind the spacecraft. Voyager has crossed the heliopause, the outer boundary of our sun's influence, the place where the solar wind, that constant stream of charged particles blown outward from the sun for 5 billion years, finally stops. Beyond this line, the sun does not rule anymore. The galaxy does. But confirming that is harder than it sounds. The magnetic field, which scientists expected to flip direction at the boundary, barely changed at all. The team was stunned. Some argued Voyager had crossed. Others said not yet. The debate lasted more than a year. Then the bunny ears settled it. In October and November of 2012, and again in April and May of 2013, the plasma wave subsystem picked up those first rising tones, those ghostly whistles. When scientists calculated the density those whistles implied, they got a number that ended the argument. 0.055 electrons per cubic centimeter. That sounds like almost nothing. And in one sense, it is almost nothing. But in the region just behind Voyager, inside the sun's protective bubble, the plasma density was about 0.002. Voyager had flown from one side of an invisible wall to the other, and the matter around it had become 20 to 30 times thicker. 6 years later, Voyager 2 confirmed it. On the 30th of January, 2019, its plasma wave instrument detected almost exactly the same density, 0.039 electrons per cubic centimeter, give or take. The same kind of jump, the same wall, 2 different spacecraft, crossing at different points, seeing the same thing. Our solar system ends at a density cliff. Think of it like a diver moving through water and suddenly hitting a thermocline, where the water temperature drops sharply, or a hiker stepping out of a heated cabin into freezing mountain air. The transition is real, and it is physical, and your body would feel it if you were there. Voyager's instruments felt it, and what they felt raised more questions than it answered. Why is the jump so sharp? What holds it in place? What keeps the denser interstellar plasma outside from rushing in, and what keeps the sparser solar plasma from rushing out? The answer involves pressure. The sun is constantly blowing outward. The galaxy is constantly pressing inward. The heliopause is the exact line where those two forces match. A balance point. A standoff that has held, more or less, for billions of years. But balance is not the same as stillness. That boundary flexes, it ripples. Solar storms push it outward for a while. Changes in the galactic environment push it inward. It is a living shoreline, not a fixed wall. And on both Voyager spacecraft, the instruments showed something even stranger happening just past the crossing. The density did not simply stabilize on the other side. It kept rising, 0.1 electrons per cubic centimeter. That is the number scientists now quote for the local interstellar medium. To most people, it means nothing. It sounds like a rounding error, a footnote in a physics textbook. So let's translate. A cubic centimeter is about the size of a sugar cube. Imagine holding one in your palm. Now imagine that inside that tiny volume, there is one single electron, just one, floating alone, nothing else to touch, nothing else to bump into. Compare that to the air in the room you are in right now. In that same sugar cube of air, there are roughly 27 million trillion molecules, 27 with 18 zeros after it, each one colliding with its neighbors billions of times every second. Air is chaos. Interstellar space is solitude. If you could somehow shrink down and stand inside the medium Voyager is flying through, you would see nothing, feel nothing. The matter density is so low that for human senses, it would be indistinguishable from perfect vacuum. And yet, across the vast distances between stars, that tiny density adds up to something staggering. Picture a tube 1 inch wide, stretching from the Sun to the nearest star, Proxima Centauri. That is a distance of about 25 trillion miles. Inside that narrow tube, at the density Voyager has measured, you would have roughly enough hydrogen to fill a small water bottle. One water bottle, across 4 light years. That still sounds like nothing. But expand the tube. Now make it the width of the entire solar system. Now the entire width of Earth's orbit. Now imagine every cubic mile of space between here and Proxima Centauri. Suddenly, the total mass of interstellar matter in that corridor is measured in millions of tons, possibly hundreds of millions. Empty space is heavy. When you give it enough room, this is why the old picture of a perfect vacuum was so misleading. The density is low, yes, but the volume is unimaginable. And across those volumes, the matter adds up into rivers, pools, and clouds that genuinely shape the galaxy. The matter is also not just sitting still. It moves, it flows, it carries magnetic fields like a conveyor belt. It gets compressed, heated, and shocked by distant supernovae. The interstellar medium is a working environment, not a backdrop. Here is another way to picture it. Take the clearest day you have ever seen, a desert morning with visibility to the horizon. The air feels empty, but you know it is not. Now imagine making that air 1 trillion times thinner, 1 trillion times less crowded. That is roughly the density Voyager is now drifting through. Sparse, but present, everywhere. And the sparseness is part of why the discoveries are so strange. At these densities, particles almost never collide with each other. An electron can travel for years, sometimes decades, without bumping into anything. That changes the physics completely. Plasma at this density does not behave like water or air. It behaves like a ghost fluid, held together by electromagnetic forces rather than physical contact. That is how the bunny ear antennas can hear it, not through sound waves in the normal sense, through oscillations in the invisible field that links every particle to every other. It is also why scientists are so excited. Interstellar plasma at this density is almost impossible to recreate in a laboratory. You cannot build a vacuum chamber on Earth that is empty enough. Voyager is sampling an environment that, until now, could only be theorized about. And the closer researchers looked at the signals, the more they realized they were not seeing a simple, quiet medium at all. They were seeing structure, layers, movement. The faint hum was turning into a language. In 2017, 5 years after the heliopause crossing, Stella Ocker noticed something the previous teams had missed. She was a graduate student at Cornell University at the time, sifting through years of old Voyager 1 data. Most researchers had focused on the whistles, those occasional rising tones that came once a year or so, triggered by solar storms hitting the interstellar medium and making it ring. Between those events, the data looked quiet, flat, boring, but it was not quite flat. Buried in the noise, Oka found a faint, steady signal, a narrow band of plasma wave emission that never stopped. It had been there the whole time, quietly humming in the background, and nobody had noticed because it was so much weaker than the dramatic whistles. She and her team published the discovery in 2021. Persistent plasma waves in interstellar space, a continuous tone, sampled every 3 days, that lets scientists track the density of the interstellar medium with a precision nobody had thought possible. Before, they had a handful of data points per year. Now they had hundreds. The map filled in, and the map was strange. The density was not constant. It rippled, it rose, and fell in small fluctuations. Over the course of weeks, it would climb slightly, then dip, then climb again. Voyager was drifting through a medium that was alive with tiny variations, like a pond with the surface gently disturbed by unseen wind. Turbulence, the team called it. The same physics that makes a river churn behind a rock, or that makes air shake an airplane. Turbulence exists in the interstellar medium, and it exists at scales Voyager could finally measure directly. What causes it? That is where the mystery gets interesting. Some of it could come from distant supernova shockwaves, still propagating outward from star explosions that happened millions of years ago. Some could come from the sun itself, as its own magnetic ripples push against the galactic environment. Some could come from processes nobody has identified yet. The hum itself is even more puzzling. Scientists have two main theories. One idea is that the plasma is being gently excited by its own thermal energy, the natural jiggling of particles at their measured temperature. Another idea, called quasi-thermal noise, suggests the antennas are picking up electrons, zipping past them at random and generating a faint electrical ringing. Either explanation works on paper. Neither has been confirmed. For now, the hum is simply there. A signal that should not be strong enough to detect, yet is. A persistent whisper from the galaxy itself, recorded by a spacecraft launched in the year Star Wars first played in theaters. Oka has described listening to the data as eerie, the sound of the universe breathing quietly in the background, except it is not breathing exactly, it is vibrating. It is oscillating in a way that hints at deeper physics we have not yet cracked, and here is what makes it unsettling. That hum extends in every direction Voyager can sense, not a local feature, not a one-off. The interstellar medium in our region is humming continuously, everywhere, at a pitch that depends on how crowded the plasma is, which means that somewhere out past Voyager, somewhere past Voyager 2, the hum still continues. It continues in regions no spacecraft will ever reach. It fills the space between every star in the galaxy. It has been doing this for billions of years, and it will keep doing it long after every human structure has crumbled. We have been surrounded by this signal our entire existence. We just never had ears to hear it. Now we do, and the hum is only the beginning, because Voyager was also moving through something much larger, a feature of the galaxy so big that our sun has been inside it for thousands of years without us knowing. A cloud. Our sun is not sailing through empty galactic space. It is sailing through fog. The fog has a name, the local interstellar cloud, sometimes called the local fluff, half affectionately, half because the density is so low that the word cloud feels generous. It is a wisp of gas and dust roughly 30 light-years across, and our solar system has been inside it for thousands of years. Nobody knew it existed for most of human history. Our ancestors looked up at the night sky and saw stars scattered across a clean, black backdrop. There was no hint that the space between us and those stars was full of anything. No hint that we were immersed in a specific structure, one of many, with boundaries of its own. The discovery came slowly, through ultraviolet telescopes. Instruments like Hubble could see the spectral fingerprints of neutral hydrogen and helium atoms drifting between the stars. When astronomers looked in different directions, they saw the same general signature again and again, a warm, diffuse medium, about 6,700 degrees Kelvin, mostly hydrogen, about one atom in every 10 cubic centimeters, with helium making up roughly 10% of the mix, and a sprinkle of heavier elements mixed in. That is the cloud our solar system is currently inside. Voyager is now sampling its outer edge. When the spacecraft's bunny ears picked up that persistent hum, when the plasma density climbed past the heliopause, what Voyager was really detecting was the local fluff itself, the part of it that has been ionized by radiation, the version of it that has had its electrons stripped away by passing photons from nearby hot stars. So the fog is not just around us, it is being sampled, right now, by a machine we built. How fast are we moving through it? The Sun and its planets are traveling relative to this cloud at about 26 kilometers per second. That is roughly 58,000 miles per hour. The cloud is flowing past us like a slow-motion river, coming from the direction of the constellation Scorpius and heading off toward Orion. If you imagine the Sun as a small boat, the local interstellar cloud is the water we are currently sailing across. Some parts of the water are slightly denser than others. Some parts have slightly different temperatures. The boundaries where one cloud meets another are fuzzy, but real. The cloud itself is probably a remnant of older events. Astronomers think it was shaped by supernova explosions that happened in the nearby Scorpius-Centaurus region a few million years ago. Those dying stars sent out shockwaves that pushed gas and dust around, carving bubbles, piling up walls of compressed matter. The local fluff is part of that debris, an echo of violence that shaped our neighborhood before the first humans ever walked. And here is a detail that tends to surprise people. The cloud is not uniform. It is part of a larger collection called the Cluster of Local Interstellar Clouds. At least 15 distinct wisps move together through this region, each with slightly different properties. Our Sun rides one of them, but it will not ride the same one forever. In fact, our solar system is close to the edge of the local interstellar cloud, close enough that in a few thousand years, possibly 10,000, possibly 40,000, we will exit it entirely and enter a neighboring cloud called the G-cloud. A subtle crossing that will not affect daily life on Earth, but will slightly change the balance of cosmic rays reaching our planet, the shape of our heliosphere, maybe even the aurora patterns over our poles. Voyager is flying through the part of the cloud we are leaving behind, and the deeper Voyager goes, the more it reveals that this cloud has its own architecture, its own density peaks, its own currents. One of those peaks came next, and it was larger than anyone predicted. Most of what Voyager is now swimming through came from something that is already dead. Hydrogen and helium were forged in the first 3 minutes after the Big Bang. That is the raw fuel of the universe, the original matter. But the carbon, oxygen, nitrogen, and trace heavier elements sprinkled through the local interstellar cloud did not come from the Big Bang. They came from stars, specifically from dying stars. When a star runs out of fuel, it has options. Small stars swell into red giants, shed their outer layers gently into space, and collapse into white dwarfs. Big stars do it violently. They explode as supernovae, scattering their guts across light years, seeding the galaxy with the elements they cooked during their lives. The matter, drifting past Voyager right now, is a mixture of both processes. Most of it is ordinary hydrogen and helium left over from the earliest moments of time, but a small fraction of it, maybe 1% or 2%, is the recycled ash of ancient stars. Some of that ash is inside you. Every atom of carbon in your body, every atom of oxygen in the water you drink, was forged in the core of a star that died billions of years ago. The same process that seeded our local medium seeded us. We are talking fragments of a stellar graveyard. Voyager is now flying through the fresh wreckage of that graveyard. The specific cloud our solar system is inside appears to have been sculpted by a series of supernova explosions in the Scorpius-Centaurus stellar association, roughly 14 million years ago. These were massive stars, probably dozens of times the Sun's mass. When they exploded, they carved out an enormous cavity in the galaxy and pushed debris outward in expanding shells. Those shells eventually slowed, cooled, and fragmented. Some pieces settled into the cloud structures we see today. The local interstellar cloud is one of those pieces. It is cosmic shrapnel, calmed down after 14 million years of drift. The thought is strange to hold. Our Sun has spent the last few thousand years floating through the aftermath of a war. The violence is long finished. The weapons are gone, only the dust remains, and our planet, and the single spacecraft now probing that dust atom by atom. And the story goes deeper. The local interstellar cloud itself sits inside a much larger cavity called the local bubble. That bubble is roughly 1,000 light-years wide, carved by dozens of supernovae over tens of millions of years. We live inside a massive scar in the galaxy. When Voyager's instruments report the density and composition of the local medium, they are essentially reading the signature of ancient dying stars. Each atom has a history. Each was cooked inside a stellar core, forged during an explosion, flung outward at thousands of kilometers per second, and then drifted quietly for millions of years until a small, gold-plated spacecraft from Earth happened to pass through. The instruments do not know any of this history. They just count particles. But the particles remember. There is another detail researchers love to point out. The dust grains in the local interstellar cloud are not just tiny rocks. They are coated, in some cases, with complex organic molecules, carbon chains, simple building blocks of the kind of chemistry that, given the right conditions, can lead to life. The matter Voyager is flying through is, in a real sense, prebiotic, not alive, not capable of becoming alive without a lot more help, but carrying the ingredients, drifting, patient, quiet. Somewhere in this cloud, 15 billion miles from home, our spacecraft is brushing past grains of dust that might one day, somewhere else, seed a planet. And the deeper Voyager moves into it, the stronger the signature becomes. Here is what everyone expected. Voyager crosses the heliopause. The plasma density jumps. Then it stabilizes. The spacecraft settles into a quiet, uniform medium, and the data gets boring. Here is what happened instead. In the first 5 astronomical units beyond the heliopause, a distance of about 460 million miles, the density kept climbing. Not by a little, by almost a factor of 2. The plasma was already thicker than anyone had predicted, and it was getting thicker the deeper Voyager went. Scientists had no good explanation. The initial jump made sense. That was the wall itself, a boundary between 2 different environments, the sun's bubble and the galaxy beyond. You expected a discontinuity there, a sharp cliff in density. But what was causing the continued rise? Voyager was well past the wall. It should have been sampling the free interstellar medium, the open galactic environment. And the open galactic environment should have been more or less uniform at these scales. It was not uniform. It had a gradient. Imagine walking out of a dense jungle into what you expect to be a clear plain. Instead, the farther you walk, the thicker the fog becomes. The ground looks flat, the sky looks open, but something is building up around you. That is what Voyager's data looked like. The team had to go back to their models. Was this a feature of the local interstellar cloud itself? A density peak that happened to be near the heliopause, by coincidence? Or was the heliopause actually compressing the interstellar medium in front of it, like a boat piling water up at its bow? The second idea turned out to be closer to the truth. Our sun plows through the galaxy at roughly 52,000 miles per hour relative to the local interstellar cloud. As it moves, its magnetic bubble pushes against the material in its path. That push creates a pile-up zone just outside the heliopause, where the interstellar plasma is compressed, densified, slowed down. Voyager flew straight through that pile-up zone. The ramp scientists saw was not the natural density of the galaxy. It was the galaxy being squeezed by our sun, a shockwave of sorts, a gentle one, not sudden enough to count as a true bow shock, but firm enough to measure. By the time Voyager reached about 160 astronomical units from the sun, roughly 15 billion miles, the density had risen to about 0.12 electrons per cubic centimeter, solidly in the range expected for the pure local interstellar cloud. The pile-up had ended. The spacecraft was finally sampling the medium in its natural state, or so the team thought. Because the density did not quite settle, it kept fluctuating, in small, irregular waves, sometimes up, sometimes down. Those fluctuations turned out to be the turbulence mentioned earlier, the tiny churning motions in the interstellar plasma itself. So the picture that emerged was stranger than anyone had pitched in textbooks. Interstellar space is not uniform. It has walls, and behind the walls it has pile-up zones. And behind the pile-up zones it has turbulent currents, and behind those currents it has a baseline density that varies from region to region depending on where you are in the galaxy. Voyager had to travel for years, at 38,000 miles per hour, to move through just one section of this structure. Every layer was a surprise, and while the bunny ears were mapping the density, another instrument on board was feeling a different force altogether, a colder force, one that operated on different rules. Pressure. You might think the matter outside the sun's bubble would be a furnace. It is not. Interstellar plasma in the local interstellar cloud is cold compared to the plasma inside our solar bubble. Inside the heliosphere, the solar wind runs at temperatures near 100,000 Kelvin in some regions, heated by its own violent outflow from the sun. Outside, the local medium sits at around 6,700 Kelvin, still hot by human standards, but far cooler than the solar wind. And yet the colder plasma pushes back harder. This is one of the most counterintuitive facts Voyager confirmed. Pressure in a plasma depends on two things: temperature and density. When you multiply them together, you get the force the plasma exerts on whatever is inside it. The interstellar plasma is cooler, but it is also about 20 times denser than the solar wind at the heliopause. 20 times the density wins. The net pressure pushes inward. That is why the sun's bubble has a boundary at all. Think of it as a cosmic arm wrestling match. On one side, the sun is blowing its plasma outward at over 1 million miles per hour, trying to expand its territory. On the other side, the galaxy is pressing inward with denser, cooler matter. The heliopause is the line where they match. If the sun got stronger, the bubble would expand. If the galaxy got denser, the bubble would shrink. Both things have probably happened over the sun's lifetime. Voyager 2 was able to measure the temperature of interstellar plasma directly because its plasma sensor was still functional when it crossed the heliopause. Voyager 1's equivalent instrument had failed years earlier, so Voyager 2 gave us something its twin could not. The numbers came back at about 30,000 to 50,000 Kelvin near the crossing, warmer than the bulk local cloud, but still cooler than the hot interior of the sun's bubble. This hotter layer right at the edge is thought to be a transition zone, where interstellar plasma gets compressed and heated by the push against the heliopause. Layered environments. Again, nothing in interstellar space is simple once you look closely. Here is another way to picture the pressure balance. Imagine a hot air balloon rising into the atmosphere. The hot air inside keeps the balloon inflated because it pushes outward against the cooler, denser air outside. If the hot air cools, the balloon collapses. If the outside air thins, the balloon expands. Our solar system is a hot air balloon made of plasma. The sun is the flame. The interstellar medium is the outside air. The heliopause is the skin of the balloon, and like any balloon, the skin is not rigid. It flexes. During periods of high solar activity, when the sun is throwing off more mass in solar wind, the balloon inflates. The heliopause pushes outward. During quieter solar cycles, the balloon shrinks. Voyager 1 and Voyager 2 both crossed during different solar conditions, which may be part of why the exact crossing distances were slightly different. The galaxy is not a passive partner either. If our solar system moves into a denser part of the local interstellar cloud, the outside pressure rises and the balloon contracts. When we exit into the sparser G cloud in a few thousand years, the balloon will expand. The heliopause will move outward, possibly by hundreds of astronomical units. Earth will not notice, but the cosmic ray environment of the inner solar system will change slightly. More galactic radiation will reach the inner planets. Less will be blocked. All of this was invisible until Voyager. And inside all of it, one feature of the interstellar medium refused to behave the way theory predicted. A feature that shook the confidence of every physicist who had modeled this region. The magnetic field. Here was the prediction. When Voyager crossed the heliopause, the direction of the magnetic field should change sharply. Inside the sun's bubble, the field points in one direction, shaped by the sun's rotation. Outside, in the galactic environment, the field should point in a completely different direction, shaped by whatever forces produced the local interstellar cloud. The flip was supposed to be the final proof of the crossing, the cleanest signal scientists could hope for. It never happened. When Voyager 1 crossed in August 2012, its magnetometer measured the field strength doubling, which was expected, but the direction barely moved. It shifted by only about 2 degrees. For a boundary that was supposed to mark the end of the sun's magnetic influence, 2 degrees was bewildering. For over a year, the team argued about what this meant. Some researchers refused to call the crossing official because the magnetic field had not flipped. Others said the other indicators, the cosmic rays, the plasma density, the disappearance of solar particles, were more than enough. Voyager had crossed, the magnetic field just was not cooperating with the models. Eventually, a new idea took hold. Maybe the sun's magnetic field and the local interstellar field happened, by pure coincidence, to be pointing in nearly the same direction at the crossing location. Not identical, but close. Close enough that Voyager could pass from one to the other without seeing a dramatic change in direction. If that was true, it was a remarkable piece of luck. Or more likely, it was a sign that the boundary region is more complicated than anyone had modeled. Maybe the solar magnetic field leaks outward. Maybe the interstellar field drapes itself around the heliopause like a sheet over a ball, conforming to the sun's influence for some distance. Maybe both. Voyager 2 complicated the picture further. When it crossed in 2018, 6 years later, and in a different direction from Voyager 1, its magnetic field did show a change. But again, not the dramatic flip theorists had expected. A shift, yes, but modest, and in a direction that did not quite match predictions. 2 spacecraft, 2 crossings, 2 different stories, both consistent with the heliopause being real, neither consistent with the older models that treated it as a clean magnetic discontinuity. This matters. The shape of the heliopause depends on the interplay between the solar and interstellar magnetic fields. If those fields are behaving in unexpected ways at the boundary, then the shape of the bubble itself might be different from what textbook diagrams show. Some researchers now think the heliopause looks less like a sphere and more like a croissant, or a deflated balloon, or a teardrop with rippling edges. The old picture, a smooth comet-shaped cocoon with a long tail streaming behind us, is being rewritten. Voyager's magnetometer data is at the center of this rewrite, and here is what makes it spooky. The instruments are measuring a magnetic environment that no one has ever been able to test in a laboratory. The densities are too low, the volumes are too vast. The only way to study this physics is to fly a machine into it and listen. The Voyagers are the only machines that have ever done this. Their data is not just one of many datasets. It is the dataset. Everything we know about in situ magnetic fields beyond our solar bubble comes from these 2 specific spacecraft, launched in 1977, powered by nuclear batteries that are slowly dying. When they go silent, that window closes. And no other mission is currently funded to reopen it for decades. Whatever the magnetic field is doing out there, the Voyagers are our only witnesses. And beyond the magnetic field, another population of particles was streaming past the spacecraft. Particles that had been held off from our solar system for 5 billion years. Particles our sun had been shielding us from our entire evolutionary history. Now they were flooding in. A galactic cosmic ray is a single particle, usually a proton, moving at nearly the speed of light. That is all it is, one proton. But at those velocities, it carries an enormous amount of energy. When it hits something, it shatters atoms, it breaks molecules, it rips through DNA. It is a bullet, fired from somewhere deep in the galaxy, and it has been traveling for maybe millions of years before arriving at its target. The galaxy is full of these bullets. Supernovae produce them. Exploding stars accelerate particles to relativistic speeds and spray them in every direction. Some come from even more exotic sources, like pulsars or active galactic nuclei. They fill interstellar space, crossing and recrossing the galaxy on timescales of tens of millions of years, and our sun has been stopping most of them before they reach Earth. The sun's magnetic bubble, the heliosphere, acts as a shield. Charged particles coming in from interstellar space get deflected by the magnetic field. The faster they move, the harder it is to deflect them, but the Sun still knocks a significant fraction of them off course. The inner solar system sees perhaps 20 to 30% of the galactic cosmic ray flux that the local interstellar cloud itself experiences. Voyager confirmed this the moment it crossed the heliopause. Cosmic ray detection rates spiked. Suddenly, dramatically, inside the heliopause, the background rate of cosmic rays had been relatively low, suppressed by the Sun's shielding. Outside, it jumped to the baseline level of the unshielded interstellar medium. That was another indicator, alongside plasma density, that Voyager had truly crossed into a new environment. The cosmic ray data also revealed something puzzling. The spectrum of energies was different from what theorists had predicted. More low-energy cosmic rays were present than expected. These are particles that the Sun's bubble is particularly good at blocking. Voyager was seeing a population that almost never reaches Earth. For the first time, scientists had a direct sample of the galactic cosmic ray population in its native environment, not the filtered, modified version that trickles through to the inner solar system, the raw version. This matters for life on Earth. For 5 billion years, our planet has evolved under the Sun's shield. The mutation rate, the rate at which genetic damage accumulates in living cells, is partly determined by cosmic ray flux. Without the heliosphere, Earth would experience more radiation at the surface. Evolution would have proceeded differently. Some researchers argue that brief reductions in the Sun's shielding, caused by passing through denser interstellar regions, might have influenced the timing of certain extinction events or evolutionary bursts. This is speculative, but the logic is sound. Cosmic rays are not harmless. They affect atmospheres. They affect clouds. They affect genetics. The shield matters. And the shield is not permanent. The Sun will eventually die. Billions of years from now, it will swell into a red giant, and its solar wind will change completely. The heliosphere as we know it will collapse. Any life still present on Earth, or on planets around other dying stars, will be exposed to a much harsher cosmic environment. Voyager is giving us an early preview of what that looks like. The spacecraft is now effectively in the unshielded radiation environment of interstellar space. Its instruments are absorbing the full flux. Its components are slowly degrading from the bombardment. Even so, it keeps functioning. The engineers who built it knew it would face this environment eventually. They did not know it would last this long. Every data point the cosmic ray subsystem returns today is a window into a galaxy our planet has never fully experienced. Particles born in stellar explosions hundreds of light years away. Particles older than our entire civilization. Particles that have been waiting for something from Earth to meet them. And when Voyager finally sent back images of this environment in data form, it revealed something else. Something that hinted the heliopause is not a smooth boundary at all. It is seething. Imagine a pot of boiling water, not the smooth surface before it boils. The chaotic surface during the rolling boil, when bubbles form, rise, collide, and burst in random patterns. That is what the heliopause might look like from the right angle. Before the Voyagers reached the boundary, most models depicted it as a smooth surface, a clean shell shaped like a teardrop, separating solar plasma from interstellar plasma. Inside, the Sun's domain. Outside, the galaxy. A tidy picture for textbooks. The data did not agree. In the region just inside the heliopause, Voyager 1 detected strange structures, pockets of differently behaved plasma. Regions where the magnetic field twisted and tangled in ways that did not match the smooth surface model. Some researchers started calling them magnetic bubbles. Others used the term magnetic foam. The idea, still being refined, is that the heliopause is not a single boundary but a frothing layer of closed magnetic loops. As the Sun's magnetic field reaches the edge of the bubble, it does not just flatten against the interstellar field, it pinches off. It forms enclosed regions, some as wide as an astronomical unit or more, that float like cells in the boundary zone. Inside each cell, plasma is trapped. The magnetic lines loop back on themselves. Particles bounce around inside. Cosmic rays from outside can leak in through the gaps between cells. That would explain why the boundary is not a clean one. It is porous. It is alive with structure. This is a new idea. A decade ago, nobody had proposed magnetic bubbles in the heliopause region. The Voyager data forced the concept into existence. Picture it from the outside. The sun's bubble is not a smooth beach ball. It is a boiling blob with foamy edges constantly forming and reforming. Solar plasma sometimes escapes through the gaps. Interstellar plasma sometimes leaks in. The boundary is closer to a battleground than a wall. This changes a lot of things. For one, it means the shielding from galactic cosmic rays is not uniform. In some places, the boundary is thick and effective. In others, it is thin and leaky. The inner solar system gets slightly more radiation in certain directions, slightly less in others. This might even fluctuate over decades as the magnetic bubbles form and dissolve. For another, it means the shape of the heliopause is probably more dynamic than the old diagram suggested. Not a static teardrop, a pulsing, shifting, foaming structure. If you could film it in time-lapse over centuries, you would see its surface crawl. The instruments that detected these features were again the same ones. Voyager's magnetometer, its cosmic ray subsystem, and the faithful bunny ear antennas. None of them were designed for this kind of discovery. They were planetary instruments, retrained by circumstance and distance to study something their creators never imagined. How big are these magnetic bubbles? The estimates vary, but some appear to be about 100 million miles across, roughly the distance from the Sun to Earth. Each one is a self-contained magnetic island drifting in the boundary zone, slowly interacting with its neighbors. If you could stand on one, you would see nothing. The plasma is too thin, the particles too sparse. Your eyes would report a perfect vacuum, but your instruments would tell you otherwise. The magnetic field lines would weave around you like invisible threads, curving back into loops, holding the structure together. Voyager is now well past this froth. Its current environment is the open interstellar medium beyond the magnetic bubbles, but the data it collected during the crossing period remains some of the richest ever gathered about the heliosphere's outer skin, and the researchers studying that data have started to suggest something that makes the whole picture even more unsettling. The wall of our solar system might not be a single feature. It might be layered, much deeper than we thought. Here is what the old textbooks said. The heliopause is a thin boundary, a surface, essentially. On one side, solar wind. On the other, interstellar medium. Cross it, and you are done. Here is what Voyager showed. The boundary is not a surface. It is a region. When Voyager 1 approached the heliopause, it entered a strange zone starting around 113 astronomical units from the Sun. The solar wind slowed dramatically. The magnetic field doubled in strength. High-energy electrons from the galaxy increased by a factor of 100. This was not the crossing yet. This was a preview. NASA scientists nicknamed it Cosmic Purgatory, a place where the Sun's influence was weakening but not gone, and the galaxy's influence was growing but not yet dominant. A transition region, a no man's land. Voyager spent months in that purgatory before finally crossing into true interstellar space. Voyager 2 saw something similar in 2018, a stagnation region, a bumpy ride through a structured boundary, not a sharp line, a layered one. The implication is significant. The wall of our solar system is not a thin skin. It is more like a castle wall, with an outer moat, an inner fortification, and several intermediate layers. Each layer has its own physics. Each reacts differently to what is flowing in and what is pushing out. Imagine it like this. You are flying a boat toward a coastline. Long before you see the beach, you notice the waves changing. The water gets choppier, then smoother, then choppy again. You hit a zone where the current pushes you sideways, then another where it pushes you forward. You feel shifts in temperature, in salinity, in the smell of the air. By the time you actually land, you have passed through an entire environmental gradient. Voyager flew through that kind of gradient at the edge of the Sun's bubble, and the gradient was thicker than anyone modeled in the pre-mission era. This has real implications. For example, it affects how we interpret signals from nearby star systems. If our Sun's boundary region is this complex, Other stars probably have similarly complex boundaries. That means the interstellar medium is peppered with these layered structures, each one sculpted by the particular star at its center. The space between stars is not just empty vacuum, it is a tapestry of interacting bubbles, each with its own wall. Some bubbles overlap, some collide, some drift apart. The galaxy is covered in them, the way a pond's surface is covered with ripples from different sources. Now imagine alien civilizations, if any exist, looking out from their own stellar bubbles. They would see their own heliopauses, their own stagnation regions, their own cosmic purgatories. And if they ever sent spacecraft through their boundaries, they would see similar layering, similar surprises in the magnetic field behavior. Voyager has given us the first in-situ tour of one of these walls. It is detailed. It is strange. It took longer to cross than anyone expected, and one feature of that wall turned out to be even weirder than the layered structure. A region where the solar wind simply stopped moving. A cosmic dead zone, right at the edge of our home. Solar wind is fast, between 1 million and 2 million miles per hour, depending on conditions. It pours out of the sun in every direction at all times, creating the pressure that inflates the heliosphere. But in 2010, Voyager 1 detected something impossible. The solar wind stopped, not weakened, not slowed by a little. Stopped. The radial velocity of the outward flowing plasma dropped to essentially zero. It was as if Voyager had reached a wall, but the wall was still 85 astronomical units inside the heliopause. The team was baffled. They called this region the stagnation region. Its inner edge sits at about 113 astronomical units from the Sun. Its outer edge blends into the heliopause itself. Inside it, the Sun's plasma has lost most of its outward momentum. It is still there. It is still charged, but it is not flowing anywhere. Something is holding it in place. That something is probably the interstellar medium, pushing inward just as hard as the solar wind is pushing outward. At the stagnation region, the two forces balance. The solar wind slows, spreads out sideways, and eventually turns around. It becomes part of a slow, recirculating flow at the edge of the bubble. Imagine a river meeting the ocean at a tidal estuary. The fresh water flows outward, but as it encounters the denser seawater, it slows, fans out, and eventually gets pushed back. Some of it mixes, some of it retreats. The result is a zone of still, murky water, where neither the river nor the ocean truly dominates. That is the stagnation region. Inside it, strange things happen. The magnetic field intensity doubles. High-energy electrons from the galaxy, which normally cannot penetrate deeply into the sun's bubble, suddenly increase by a factor of 100. Particles from inside the heliosphere, which should be streaming outward, start flowing sideways instead. It is a kind of cosmic eddy, a slow, circulating region where the outward march of the sun's plasma finally breaks down. Voyager 1 spent nearly 2 years in this zone before finally crossing into the true interstellar medium. The detector readings from those years are among the most unusual ever collected. Scientists are still analyzing them. One of the puzzles is how stable the region is. It does not seem to be just a temporary feature. It appears to be a structural component of the heliosphere, always present, always fluctuating slightly but never collapsing. The sun's outward pressure has been matched against the interstellar inward pressure for billions of years, and somewhere near that balance line, the stagnation region has existed the whole time. This has implications for what the inner heliosphere looks like. If the outer edge is this complex, the flow of solar wind throughout the entire bubble must be more intricate than the simple outward expansion model suggests. Some researchers have begun to describe the heliosphere as a giant, slowly churning reservoir of plasma, with the stagnation region acting as a kind of backflow dam at its outer edge. For anyone who still thinks of the sun's bubble as a simple expanding balloon, the stagnation region is the counterexample. It is the part that does not expand, the part that sits still, the part that, in its own quiet way, holds the whole structure together. Voyager 2 saw a similar stagnation region during its own crossing, though with slightly different characteristics. That confirmed the feature is real, not a fluke. Every star system with a bubble, probably has one. Past the stagnation region, past the heliopause, past the density ramp, Voyager finally entered the open interstellar medium. What came next seemed almost peaceful by comparison. But peace in space is an illusion, because drifting through the local cloud, unseen by any camera, invisible to every instrument on board, was something else, something physical, something the spacecraft was now colliding with, atom by atom, every moment of every day. Dust. Voyager has no dust detector. That is an odd thing to say about a machine flying through a cloud of interstellar dust, but it is true. The original mission design did not include an instrument for cataloging grain impacts in the interstellar medium. The engineers of the 1970s never expected Voyager to be in the interstellar medium long enough for that to matter. And yet, grains are hitting it. The local interstellar cloud contains tiny solid particles mixed in with the gas. These grains are incredibly small. Most are only a fraction of a micrometer across, smaller than a bacterium, smaller than a wavelength of visible light. They are the residue of dead stars, the condensed remnants of elements heavier than helium, coated in some cases with layers of ice and organic molecules. Their density is stunningly low, roughly 1 grain per cubic kilometer, give or take, depending on where you are in the cloud. For comparison, the air in front of your face probably contains more dust particles than a cubic mile of interstellar space. But Voyager is moving fast. At 38,000 miles per hour, relative to the local cloud, the spacecraft sweeps out a large volume of space every year. Over the decades, it has undoubtedly been struck by many individual grains. Each strike is a miniature collision, delivering a small amount of energy to the spacecraft surface. Most strikes leave no detectable trace. The grains are too small, the energies too low to register on any instrument Voyager carries. But if you could examine the spacecraft up close, after its decades in interstellar space, you would find tiny pits, microscopic craters, the signature of countless silent collisions with dust no one on Earth will ever directly sample. Future missions might. Several proposed interstellar probes would carry dust detectors specifically tuned to interstellar grain impacts. By measuring the mass, velocity, and composition of individual grains, these missions could reconstruct the history of the local interstellar cloud in unprecedented detail. Was the cloud enriched by a specific supernova? Does it contain grains from asymptotic giant branch stars? What fraction of its carbon is in solid form versus gas? For now, all we know comes from remote observations. Astronomers detect the presence of dust by measuring how it scatters and reddens starlight. When you look at the color of a distant star, some of the blue light has been removed by dust grains along the path. The redder the starlight appears, the more dust has been absorbed. This technique has let us map the rough distribution of dust in the local interstellar cloud. It has also let us measure the sizes of the grains, since different sizes affect different wavelengths of light. The result is a statistical picture, not sample by sample, but average properties. Voyager is flying through this dust right now, silently, constantly, every day of its remaining life. In a sense, the spacecraft is becoming the dust. Tiny pieces of it are being eroded, microscopically, by each grain impact. Its gold-plated surfaces are being abraded. Its aluminum structure is being pitted. None of this threatens the mission in any meaningful way. But it is happening, and it will continue to happen long after the spacecraft stops transmitting. In 10,000 years, Voyager will still be drifting through dust. In 100,000 years, still. In 1,000,000 years, still. The grains it encounters in the far future may come from stars that have not been born yet, cooked in explosions that have not yet happened, scattered through regions of the galaxy Voyager will only barely begin to reach. The spacecraft will become a time capsule, preserved at low temperatures, slowly sculpted by interstellar dust, carrying its recording of Earth and the sounds of our civilization into an indefinite future. Whatever finds it, if anything ever does, will find a machine that has been bathed in the same matter Voyager was trying to describe. And that matter, it turns out, is not evenly distributed. It is clumped, structured, shaped by forces we are only starting to understand. forces that hint at something much larger than the cloud itself. When Voyager 1 and Voyager 2 compared their measurements, a pattern emerged that had not been obvious from either spacecraft alone. The plasma density Voyager 2 measured was slightly different from what Voyager 1 had measured. Not by much, but the difference was consistent. And more importantly, the way each spacecraft saw the density change as it moved outward was not identical. Voyager 1 is moving roughly toward the direction called the nose of the heliosphere, the front side of our solar bubble, the part that faces into the galactic wind as the sun plows through the local cloud. Voyager 2 is moving in a different direction, more toward the flank. The two spacecraft are sampling different parts of the outer heliosphere, and beyond, different parts of the local interstellar cloud. By comparing their density measurements, scientists can map a large-scale gradient in the interstellar medium. That gradient exists, and it tells us something about the shape of the bubble itself. In the direction Voyager 1 is heading, the density rises more steeply. In the direction Voyager 2 is heading, the rise is gentler. This is consistent with the heliosphere being compressed in front, stretched out behind, like a raindrop falling through air. The nose is squashed, the tail is elongated, but the picture is more nuanced than a simple teardrop. Some models now suggest the heliosphere is shaped more like a croissant. Not a long tail, but a relatively compact blob with curved flanks. Other models suggest a long comet shape. The disagreement comes from different assumptions about the interstellar magnetic field and how strongly it deforms the bubble. Voyager is the tiebreaker. Its data is pushing the modelers towards certain shapes and away from others. The current best guess is something between a croissant and a teardrop, with a complicated boundary that varies in thickness around the bubble. Why does this matter? Because the shape of the heliosphere determines how much of the galactic environment reaches the inner solar system. A longer tail means more regions where cosmic rays might leak in from behind. A compressed nose means more shielding in front. If our sun moves into a denser interstellar region, the nose squashes further. The shielding in front increases. The tail might lengthen. Earth's cosmic ray environment depends on this geometry. There is also a deeper implication. Every star has a similar bubble, shaped by its own stellar wind and the surrounding interstellar medium. If our sun's bubble is asymmetric, other stars' bubbles are asymmetric too. The galaxy is dotted with these odd shapes, each one sculpted by its particular star and its particular patch of gas. When astronomers look for habitable planets around other stars, they consider these factors. A star with a weak bubble might expose its planets to more cosmic radiation. A star moving through a dense cloud might have a heavily compressed heliosphere. Life, if it exists elsewhere, is partly regulated by the shape and strength of its local stellar bubble. Voyager is the only direct measurement we have of one of these structures. Every other bubble in the galaxy is known only through indirect methods. Optical observations, ultraviolet spectra, models. Our sun's bubble, mapped in detail by the Voyagers, is the template. And the template is not simple. It is layered. It is asymmetric. It has density gradients. It has stagnation regions. It has magnetic foam. It has walls that are not walls, but thick layered zones. Our understanding of this object, the object we live inside, has been transformed by two small spacecraft that launched before most of the scientists studying them were born, and the map is still being drawn. Every week, the Voyagers send back a little more data. Every month, a new paper refines what we know. Every year, another layer of the picture sharpens. But the spacecraft are aging. Their power is fading. The window for direct measurement is closing. And beyond that window, the galaxy keeps its secrets. Zoom out from the local interstellar cloud, and you find something even bigger. A cavity, roughly 1,000 light-years across, nearly empty compared to the space around it. Our solar system sits near its center, along with most of the stars you can see with the naked eye. Astronomers call it the local bubble. It is a hole in the galaxy, a hollow region where the density of gas and dust drops dramatically compared to the spiral arm material around it. For decades, the local bubble was a mystery. Why is it here? What carved it? Why is our sun near its center? The answer turned out to involve a story of serial violence stretching back millions of years. Around 14 million years ago, a cluster of massive stars began dying. One by one, they went supernova. Each explosion released more energy in a few weeks than the Sun will release in its entire 10 billion year lifespan. Each blast swept material outward in a shockwave, heating gas to millions of degrees and pushing it away at hundreds of miles per second. These shockwaves collided. They merged. They compressed matter at their edges and evacuated matter from their interiors. After many explosions, the result was a single, enormous cavity carved into the galaxy by overlapping supernovae. That cavity is the local bubble. Recent research led by Catherine Zucker at Harvard has identified the likely source, a stellar nursery called the Scorpius-Centaurus OB Association. Over the last 14 million years, roughly 15 supernovae detonated in that region. Their combined energy was enough to blow out a 1,000 light-year cavity in the galactic disk. The compressed shell around that cavity is where new stars are forming today. Many of the nearest young stellar nurseries, including the Taurus, Orion, and Perseus regions, sit on the outer edge of the local bubble. They are literally the compressed debris of those ancient explosions, collapsing into new stars. Our Sun is a visitor. It did not form inside the bubble. It was elsewhere in the galaxy when the supernovae happened. Over the last few million years, the Sun's orbit around the galactic center has carried it into the local bubble, and we are now passing through the hollow interior. Inside the bubble, the density of gas is astonishingly low, perhaps 1/100th of the density of a typical spiral arm region. In some places, perhaps less than 1,000th. Voyager is flying through one of the denser patches inside the bubble, the local interstellar cloud itself. But the surroundings are sparser still. This is why our view of the galaxy is so clear. If our solar system were inside a denser part of the Milky Way, interstellar dust would block much of the starlight. Many of the stars and nebulae we take for granted would be invisible. The local bubble gives us a window, a cleared-out vantage point from which to see outward. Astronomers have started to realize how lucky this is. A civilization emerging inside a dense interstellar region might never discover the structure of its galaxy, because it could never see through the dust. A civilization emerging inside the local bubble, like ours, gets a panoramic view. The local bubble is also still growing. The debris from those old supernovae is still expanding, still pushing outward at around 4 miles per second. The bubble's boundary is a slow-motion explosion, frozen on the timescale of a human life, but moving perceptibly over millions of years. Voyager is sampling matter inside this bubble, matter that was, in some cases, blown into its current position by shock waves from dying stars, matter that carries the chemical fingerprints of those explosions. And our Sun is not going to stay in this particular region forever. In a few tens of thousands of years, we will pass from the local interstellar cloud into a neighboring wisp of gas. The sky will not change. The stars will look the same. But the environment our solar system breathes will shift. The local interstellar cloud is not our forever home. Our solar system has only been inside it for the last few tens of thousands of years. Before that, we were in a different region of the local bubble, possibly a nearly empty zone with even lower density. The cloud drifted across our position, or we drifted into the cloud, depending on how you want to frame it, and we will exit it. Astronomers estimate that in somewhere between 5,000 and 40,000 years, the Sun will move out of the local interstellar cloud and into a neighboring cloud called the G cloud. The G cloud sits in the direction of Alpha Centauri, the nearest star system to ours. It has slightly different properties from the local interstellar cloud, slightly different density, slightly different temperature, slightly different magnetic field orientation. The transition will happen smoothly. There is no sharp wall between the local interstellar cloud and the G cloud, just a fuzzy boundary zone where one fades into the other. Earth will not notice. The Sun will not notice. No one alive during the crossing will be able to point at a moment and say, "Here is where it happened." But the cosmic ray environment of the inner solar system will shift. The G cloud is thought to be slightly less dense than the local interstellar cloud. If that is correct, the heliosphere will expand when we enter it. The Sun's bubble will inflate a little, pushing the heliopause outward by tens or hundreds of astronomical units. The shielding against galactic cosmic rays will improve. The radiation reaching Earth's atmosphere from the galaxy will drop slightly. Over long timescales, this kind of shift can have measurable effects. Some geological records suggest that cosmic ray flux has varied over the last few million years, and at least some of that variation may be tied to the Sun's journey through different interstellar environments. Imagine our solar system as a ship, and the clouds as patches of different weather. Sometimes we pass through storms, sometimes clear air, sometimes misty, foggy regions. The ship is always moving. The weather is always changing. And the history of our Sun's journey has been eventful. Over the last several million years, we have passed through at least a few distinct clouds, maybe more. Some were denser, some were sparser. Some had higher magnetic fields. Each transition affected the shape of the heliosphere and the cosmic ray environment of Earth. One intriguing theory suggests that around 2 to 3 million years ago, the Sun passed through a particularly dense interstellar cloud. The heliosphere would have been severely compressed, possibly even pushed inside the orbit of Earth. If true, Earth would have been exposed to nearly unshielded interstellar matter for an extended period. Some researchers have linked this to possible evolutionary pressures on early hominins. This is still speculative. The evidence is indirect, but the idea is real. Our evolutionary history might be partly shaped by the interstellar environment our solar system has drifted through. Voyager is not going to reach the G cloud on any human timescale. The spacecraft is moving at about 38,000 miles per hour, which is fast, but the distances involved are cosmic. By the time Voyager might be entering the G cloud region, it will have been silent for tens of thousands of years, battered by interstellar dust, frozen at temperatures near absolute zero. The transition will happen around the Sun, not around Voyager. Earth's descendants, if any still exist by then, will witness the shift firsthand. For now, we are riding the local interstellar cloud. Voyager is probing its outer edge. The sky looks the same as it ever did, but the ground beneath our ship is moving, and the cloud is drifting past us, and someday soon we will be somewhere else. Between the big whistles and the steady hum, Voyager found something else. Small ripples, tiny fluctuations in the density of the interstellar plasma, happening on scales of astronomical units or smaller. When Stella Ocker and her team analyzed the continuous plasma wave data, they saw these fluctuations clearly. The density was not smooth. It was lumpy. This is turbulence. Not the violent kind you feel on a plane in bad weather, but the same basic physics. In any fluid, when different regions move at different speeds or carry different densities, the fluid develops eddies and swirls. These eddies cascade down to smaller and smaller scales, eventually dissipating as heat. Interstellar plasma turbulence works the same way, but with a twist. The plasma is so thin that ordinary collisions between particles do not matter much. Instead, the turbulence is carried by magnetic fields. Waves in the magnetic field push charged particles around, creating density variations that ripple across vast distances. Voyager is now measuring these ripples directly. For the first time, scientists have a nearby sample of what interstellar turbulence actually looks like. The fluctuations are small, a few percent variation in density over scales of a few astronomical units, but they are real, and they persist, and they match theoretical predictions of how plasma turbulence should behave in the local medium. Why does this matter? Because turbulence in the interstellar medium does a lot of important work. It helps mix elements produced by dying stars into the surrounding gas. It affects how cosmic rays propagate through the galaxy, scattering them off magnetic irregularities. It shapes the way new stars form, because turbulence can either support a gas cloud against collapse or help it fragment into smaller pieces. Everything about the galaxy's long-term evolution depends on how turbulence works in the interstellar medium. And until Voyager, we had no direct in-situ measurements to compare against our theories. Now we do, and the theories mostly hold up, with some interesting refinements. The turbulence spectrum Voyager measured looks similar to what theorists had predicted, but with features that suggest the local plasma is slightly more compressible than some models assumed. Small details, but they matter when you are trying to understand how matter flows across a galaxy over billions of years. Picture the local interstellar cloud as a river. From far away, it looks smooth, featureless, uniformly flowing. But when you get up close, you see the surface is full of eddies, ripples, small waves traveling in different directions. None of these features is dramatic, but together, they shape how the river moves. Voyager is now up close. The river is rippling. The turbulence is there, and some of that turbulence is probably caused by events that happened millions or even billions of years ago. Shock waves from ancient supernovae are still propagating through the interstellar medium, slowly dissipating but still stirring the plasma. Waves from stellar winds of long-dead stars are still reverberating through the gas. The local medium carries the accumulated history of its neighborhood. If you could translate the turbulence into sound, it would be a low roar, the blended noise of 10,000 forgotten explosions mixed together into a single texture that fills every cubic mile of space. And mixed into that turbulence is another feature Voyager's instruments caught, a magnetic field that behaves in strange ways, one that points in a direction almost no model had correctly predicted. The interstellar magnetic field in the local interstellar cloud is weak, about 4 to 5 microgauss. For comparison, the magnetic field at Earth's surface is about half a Gauss. That is roughly 100,000 times stronger than the interstellar field. But weak does not mean insignificant. The interstellar field stretches across light years. It permeates the local interstellar cloud and the surrounding local bubble. It shapes how cosmic rays travel, how plasma flows, how the heliosphere is deformed. Over vast distances, even a weak magnetic field becomes dominant because there is nothing else exerting comparable forces. Voyager measured this field directly, and the measurements were surprising. The direction is tilted. The interstellar field does not align neatly with any obvious galactic structure. It does not point along the local spiral arm. It does not align with the nearest star-forming regions. It has its own orientation, apparently shaped by the specific history of the local bubble and the cloud structures within it. When Voyager 2 crossed the heliopause and began measuring the interstellar field, researchers compared the direction to what they had expected. The mismatch was significant. The field was stronger than predicted in the region just beyond the heliopause, about twice the strength of the average local interstellar cloud field. This hinted at something called a draped magnetic layer. The interstellar field was being distorted by the presence of the heliosphere itself. As our solar bubble moves through the local cloud, it compresses the magnetic field lines in front of it, like a boat compressing water at its bow. The result is a region just outside the heliopause where the field is enhanced and draped around the bubble's nose. Voyager 2 flew straight through that draped layer. Over time, as the spacecraft moved deeper into the interstellar medium, the field strength declined toward the undisturbed local value. Voyager was leaving the compressed region and entering the true local interstellar cloud field. That transition has been measurable in the data. One puzzle remains. The direction of the interstellar field is close to, but not identical to, the direction of the field inside the heliopause right at the boundary. This is why the magnetic field did not dramatically flip when the Voyagers crossed. The two fields are nearly aligned, possibly because the heliosphere itself has rotated or oriented itself to minimize the magnetic mismatch. That is the coincidence theory. Another possibility is that the interaction between the solar and interstellar fields at the boundary is so complex that the fields partially merge, creating a smooth transition rather than a sharp discontinuity. Either way, our solar bubble is magnetically embedded in its surroundings in a way that is more seamless than anyone predicted. Here is what that means for life on Earth. The tilted interstellar field guides cosmic rays. It channels them along certain directions and deflects them along others. Earth's sky, when viewed in cosmic ray energies, is not isotropic. There are directions where more cosmic rays come from and directions where fewer come from. These asymmetries reflect the structure of the interstellar magnetic field in our neighborhood. Voyager has helped map that field directly. Every data point the spacecraft has returned is a vote for one model or another, forcing theorists to refine their pictures of the local galactic environment. And the spacecraft keeps going, deeper into the cloud, Further from home, each year, the map gets a little more detailed, but the cloud is not silent. Remember, it is humming, and that hum raises a question that sounds almost paradoxical at first. How does sound travel through something that thin? On Earth, sound travels by molecular collision. You push air molecules, they push their neighbors, and the disturbance propagates outward at about 760 miles per hour. In interstellar space, molecular collisions are almost non-existent. A hydrogen atom can drift for years without bumping into another one. If you tried to scream in the local interstellar cloud, your voice would literally have nothing to push. And yet, Voyager detects oscillations, waves, rhythmic vibrations that behave in many ways like sound. How is that possible? The answer involves a different kind of fluid. Interstellar plasma is not a neutral gas. It is made of charged particles, electrons, and ions that interact through electromagnetic forces rather than physical contact. These charged particles can transmit disturbances across vast distances, even though they rarely touch each other. When a shock wave from a distant solar storm reaches the interstellar plasma, the first thing it does is push electrons. The electrons start oscillating at a specific frequency determined by their density. That oscillation is not sound in the traditional sense, but it is a wave that propagates through the plasma, carrying energy from one place to another. Scientists call these plasma waves. They are the primary way disturbances travel through interstellar space, and they are what Voyager's bunny ear antennas have been picking up for over a decade. If you could translate plasma waves into audible frequencies, you would hear something like a hollow ringing, a distant choir, a low moan that rises and falls. That is roughly what NASA has done with Voyager's data, shifting the frequencies into the audible range so humans can hear what the spacecraft detects. The result is strange, not quite music, not quite noise, a sound that feels ancient, because it essentially is. Plasma waves travel fast, much faster than ordinary sound. In interstellar space, they can cross astronomical units in hours or minutes, depending on their frequency. This is why Voyager can detect shock waves that originated at the Sun years earlier. The shock wave itself takes months to travel outward, but once it hits the interstellar medium, it generates plasma waves that propagate ahead of it, reaching Voyager before the shock wave itself. Those plasma waves are the whistles. They are followed, often years later, by the actual shock wave, which Voyager's magnetometer and cosmic ray subsystem can detect. The interstellar medium, then, is not silent at all. It rings constantly. Every disturbance, anywhere in the local region, generates plasma waves that spread outward, cross each other, and fill space with a background of oscillations. The hum Ocker and her team discovered is the combined signature of all these waves, summed over time. If your ears could hear plasma waves directly, and if you could stand in the local interstellar cloud somehow, you would never experience silence. The galaxy would always be whispering to you. Old shock waves, local turbulence, distant stellar explosions still echoing through the plasma. The combined voice of everything that has happened in your neighborhood of space for millions of years. Voyager is hearing that voice right now, and the voice has been continuous since the spacecraft entered the interstellar medium. Every month, the instruments report another fragment of the sound. Every year, researchers add more of the signal to their models. The galaxy was never empty. It was always speaking. We just had no way to listen until now. When the sun has a bad day, Voyager hears about it. Solar storms happen frequently. The sun throws off massive bursts of plasma called coronal mass ejections that travel outward at speeds between a few hundred and a few thousand miles per second. Most of these never affect Earth. Some of them hit our planet's magnetic field and cause aurora displays. A tiny fraction, the largest, disrupt power grids or radio communications. But all of them, eventually, reach the heliopause. And when they do, they create shock waves that cross into the interstellar medium. Those shock waves do not disappear at the boundary. They keep going, slowly weakening, slowly spreading, but still propagating outward into the local interstellar cloud. Voyager detects them when they pass over the spacecraft, sometimes months or years after the original solar event. The time lag is enormous. A solar storm might erupt at the sun in January, The coronal mass ejection travels outward for about a year, reaches the heliopause, and generates a shockwave that propagates into the interstellar medium. That shockwave travels further for several more months before passing over Voyager. By the time Voyager's instruments register it, 2 years have passed since the event that caused it. Voyager is, in a sense, a time machine. Every whistle it detects is the echo of something the Sun did years ago. The whistles also tell us about the interstellar medium itself. As a shockwave propagates through plasma of different densities, the frequency of the plasma oscillations it generates changes. By measuring those frequency changes, scientists can map the density along the path the shockwave took. Each whistle is a brief survey of interstellar plasma, conducted by the shockwave on its way to Voyager. This is how researchers first mapped the density gradient beyond the heliopause. The whistles showed a rising frequency, which meant rising density, which confirmed the pileup zone. Some of the shockwaves Voyager has detected came from specific, identifiable solar events. Scientists have been able to trace particular coronal mass ejections through Earth's data outward to Voyager's data, confirming the journey. The spacecraft functions as the outermost node of a solar monitoring network. Every major solar event eventually registers there, after a long delay. The shock waves also affect the plasma they pass through. Each shock wave compresses the medium slightly, heats it briefly, stirs it up before moving on. After many shock waves over millions of years, the interstellar medium becomes a kind of record of solar history. Modern measurements of the local cloud's turbulence and structure may reflect the accumulated effects of countless ancient solar storms. Over the long term, this is how stars influence their surroundings, not just through radiation and stellar winds, but through the accumulated impact of billions of shockwaves, each one tiny, each one leaving its trace. Our Sun has been doing this for 4.5 billion years. The local interstellar cloud has been absorbing solar shockwaves for as long as our solar system has existed, and much longer than our Sun has been inside this particular cloud. Some of the turbulence Voyager measures today may date from eras before life on Earth began, and as Voyager moves further from the Sun, the shock waves it detects will grow weaker and rarer. At some point, the spacecraft will be too far to detect them at all. The solar connection will fade. The last echoes of the Sun will fall silent. But by then, Voyager will be hearing other things. Possibly shock waves from supernovae, possibly waves from interactions between clouds, possibly signals we have not yet predicted. Every mile deeper is a new dataset. For decades, every textbook showed the heliosphere as a teardrop, a round nose facing into the galactic wind, with a long tail streaming behind. Simple, elegant, easy to draw. Then data started breaking the picture. In 2020, a team of researchers using observations from the Cassini spacecraft and the Interstellar Boundary Explorer proposed a radical alternative. The heliosphere, they argued, does not have a long tail. Instead, it has a relatively compact shape that bends back on itself, more like a croissant than a teardrop, a crescent-shaped bubble with the Sun near its center and 2 short lobes curving backward. The reason came down to magnetic fields. The interstellar magnetic field, running through the local interstellar cloud, has a specific orientation. As the solar wind streams outward and meets that field, it does not just flow past and form a long tail. The magnetic field grabs the plasma, twists it, and forces it into a compact, warped shape. If this picture is correct, the heliosphere looks nothing like the smooth teardrop shown in old illustrations. It looks like a deformed pastry, asymmetric and strange, with regions of plasma curling back toward the Sun rather than streaming out behind it. Voyager provides important evidence. The spacecraft is moving in a direction that, under the teardrop model, should take it into the long tail of the heliosphere. Under the croissant model, it should take it into one of the lobes, and eventually out into the interstellar medium much sooner than the teardrop predicts. The timing of Voyager's heliopause crossings is more consistent with the croissant model than the teardrop. Both Voyager 1 and Voyager 2 exited relatively quickly after entering the boundary region. If the heliosphere had a long tail, they should have spent much longer in transit. Debate continues. Some researchers favor the teardrop, others favor the croissant. Still others propose intermediate shapes. The truth is probably somewhere in between, with the heliosphere being a complex, time-varying structure that does not perfectly match any simple geometric model. What everyone agrees on is that the old textbook picture is wrong. The heliosphere is asymmetric. It is shorter than expected in some directions. Its boundary is layered and dynamic. Its shape depends on both the sun's current activity and the local interstellar environment. For public understanding, this is a big shift. Generations of students have been taught a picture that does not match reality. The teardrop is now a historical artifact, useful for teaching basic concepts but misleading in detail. The croissant picture has its own problems. Some observers find it too extreme based on indirect measurements that may have alternative interpretations. Others love it because it explains several previously puzzling observations. The scientific community is still working through the implications. In the meantime, Voyager keeps sending back data. Each new measurement helps constrain the models. Each year, the shape of the heliosphere comes into slightly sharper focus, and whatever shape it turns out to be, it is our home. Everything inside that bubble, every planet, every comet, every asteroid, every living creature, exists under the protection of that deformed pastry-shaped magnetic shield. Our species grew up inside that shape. Our biology evolved under its protection, and we are only now starting to see what it actually looks like. 4 light-years from the Sun, Alpha Centauri waits, our nearest stellar neighbor, a triple star system, possibly home to planets. The closest place any human probe could ever realistically visit, and Alpha Centauri is inside a different interstellar cloud. The G cloud, named for its proximity to galactic coordinates near the star Aldebaran, is a separate wisp of gas from the local interstellar cloud. Our Sun is currently near the boundary between the two clouds. Alpha Centauri is already inside the G cloud, fully immersed. This matters because the G cloud has different properties: slightly lower density, slightly different temperature, a different magnetic field orientation. The heliosphere of Alpha Centauri, if it has one, would be shaped by these different conditions. The astrosphere of Alpha Centauri A and B has been studied indirectly, and it appears to be smaller and more compressed than our own heliosphere, likely because of differences in the local environment. If any of the planets around Alpha Centauri host life, that life is evolving in a different interstellar weather system than ours. The cosmic ray flux at the surface of those planets might be different. The shielding provided by their star's bubble might be weaker or stronger. These are subtle differences, but over billions of years, they could shape biology. Our Sun is heading toward the G cloud. In some sense, we are heading toward the conditions Alpha Centauri already experiences. The crossing will take thousands of years, but it is happening. Our solar system is literally moving into our nearest neighbor's interstellar weather. Voyager cannot witness this transition. The spacecraft will be silent long before the Sun enters the G cloud, but future missions, if humanity sends any, will likely be tasked with measuring the new environment. The first generation of probes to sample the G cloud directly will be among the most important scientific tools ever deployed. There are other clouds too. Our region of the local bubble contains at least 15 distinct wisps organized into a loose cluster called the cluster of local interstellar clouds. Some are closer, some are farther. Some our Sun has passed through in the past. Some it will encounter in the future. The exact order depends on how everything is moving. Mapping these clouds is a difficult task. They are visible only through the subtle absorption of light from distant stars. Different clouds absorb different wavelengths, and by comparing spectra from many directions, astronomers reconstruct the 3-dimensional structure of the local medium. The picture is not yet complete. New clouds keep being identified. Old boundaries get redrawn as better data comes in. Every year, the map of our interstellar neighborhood improves slightly, and the map is not static. The clouds are moving. The local interstellar cloud is drifting at about 26 kilometers per second relative to the Sun. The G cloud moves at a different speed and direction. These relative motions mean the map we see today is not the map from a million years ago, and it will not be the map a million years from now. On human timescales, nothing changes. The stars rise and set as they always have. The Milky Way arches across the sky in familiar patterns, but underneath, the medium we live in is shifting, crossing, mixing. Our solar system rides these currents like a ship on an ocean whose tides are measured in millennia. Voyager is our one spacecraft navigating this ocean directly. When it goes silent, we will have to infer the rest from remote observations until something else goes out there. Cosmic rays break DNA. That is not hyperbole. When a cosmic ray passes through a living cell, it can ionize atoms along its path, damaging molecules and sometimes severing strands of DNA. Most damage is repaired by cellular machinery. Some is not. The residual damage contributes to the background mutation rate of every living organism on Earth. Over geological time, this mutation rate shapes evolution. Now, consider what happens when the interstellar environment changes. If the Sun passes through a denser cloud, the heliosphere shrinks. More cosmic rays reach Earth. The mutation rate rises. If the Sun passes through a sparser region, the heliosphere expands. Fewer cosmic rays reach Earth. The mutation rate falls. Some researchers have argued that these changes, occurring over millions of years, may have influenced the pace of evolution. Periods of high cosmic ray flux could accelerate mutation and drive rapid evolutionary change. Periods of low flux could slow things down. Evidence is suggestive but not conclusive. Paleontologists have identified certain periods in Earth's history when biodiversity changed rapidly. Some of these periods loosely correlate with times when the Sun is thought to have passed through denser interstellar regions. The correlation is not tight, and alternative explanations exist for every transition. But the possibility is taken seriously. One specific case involves a period about 2 to 3 million years ago. Evidence from ocean sediments suggests Earth was showered with iron-60, a radioactive isotope produced mainly in supernova explosions. That iron-60 probably came from one or more nearby supernovae, which would have compressed the heliosphere and potentially exposed Earth to higher cosmic ray fluxes for thousands to tens of thousands of years. That period roughly coincides with several evolutionary events among early hominins, as well as changes in climate and ecosystems. Causation remains debated, but the exposure was real. The iron is still detectable in deep-sea sediments. Earth absorbed the debris of a stellar explosion, and our ancestors may have lived through the aftermath. Voyager cannot give us a direct time machine to those events, but by measuring the current cosmic ray environment in detail, the spacecraft helps us calibrate our models of how Earth's exposure has varied over time. If we know precisely what the local interstellar cosmic ray flux looks like today, we can better estimate what it looked like during past transitions. The implications extend beyond our own planet. Any life-bearing world in the galaxy experiences cosmic ray bombardment, and that bombardment varies depending on the local interstellar environment. A planet around a star that moves through many dense clouds would see highly variable mutation rates. A planet in a quiet corner of the galaxy might see very stable conditions. This becomes relevant to the search for life elsewhere. Planets in star systems with unstable cosmic ray environments might have more variable evolutionary histories, possibly including more extinctions or more rapid diversification. Planets in stable environments might have slower but more persistent evolutionary processes. We do not know how much cosmic rays actually matter in the big picture. They are one factor among many, probably a minor one in most cases. But over billions of years, small factors add up. Voyager is giving us our first direct measurement of the cosmic ray environment outside our bubble. That measurement is a baseline. Against it, we can now interpret the cosmic ray record preserved in meteorites, lunar samples, and deep-sea sediments. The history of radiation exposure on Earth is being reconstructed in finer detail than ever before, and Voyager, the messenger delivering this data, is running out of power. Voyager is flying through a region of interstellar space that is still influenced by the Sun. That might sound wrong. The spacecraft is beyond the heliopause, beyond the density ramp, deep into what scientists call the very local interstellar medium. But even here, the sun's presence is felt. The draped magnetic field, the compressed density layer, the shock waves propagating outward from solar storms. All of these are signatures of the sun reaching out into the galaxy, modifying the interstellar environment in its immediate neighborhood. The pristine interstellar medium, the medium completely undisturbed by our star, lies much further out. Estimates vary, but the consensus is that beyond roughly 500 to 1,000 astronomical units from the sun, the interstellar medium becomes effectively pristine. At that distance, the sun's gravitational, magnetic, and plasma effects all fall below the local interstellar background. You are finally in the open galaxy. Voyager will never reach that distance while transmitting. The spacecraft is currently around 165 astronomical units from the sun and moving outward at about 3.5 astronomical units per year. At that rate, Voyager would take more than 100 years to reach 500 astronomical units. Its nuclear power supply will fail long before then. Estimates suggest the last instruments will go dark sometime in the late 2020s, after nearly 50 years of operation. By the time Voyager enters the truly pristine interstellar medium, it will be a silent artifact. Its data will have stopped flowing. The bunny ear antennas, still listening perhaps, will have no way to transmit what they hear. This is a genuine loss for science. The most interesting measurements, the ones that would tell us what interstellar space looks like without any solar influence, will never be made by Voyager. They await a future mission. Proposals for such a mission have been floated for decades. An interstellar probe, a spacecraft designed specifically to reach 500 or even 1,000 astronomical units within a human career span, carrying modern instruments optimized for interstellar science. Such a mission would need a much faster propulsion system than Voyager had, possibly using a solar sail or a nuclear thermal rocket, combined with a gravity assist from the sun. No such mission has been funded. The technology exists. The science case is compelling, but the cost is enormous, and the payoff is measured in decades. Political will to commit to missions with such long timescales is difficult to sustain. For now, we have Voyager, and Voyager, despite its limitations, has given us more than anyone could have reasonably expected. Every day, the spacecraft crosses new territory. Every measurement is the first of its kind. Every gigabyte of data is a window into a region humanity has never directly probed before. If Voyager had failed in the 1980s, the interstellar medium would still be a theoretical construct today. Our understanding would be limited to remote observations and computer models. Instead, we have real measurements, real plasma densities, real magnetic field data, real cosmic ray fluxes, real whistles and hums, captured by antennas built when disco was still on the charts. The pristine medium may wait, but the near interstellar medium, the region just past our cosmic shore, is now known in a way it never was before. And the knowing came from one spacecraft, two, counting its twin, launched together in 1977 into a mission nobody expected to last. Now they are ambassadors in a frontier no previous generation could even imagine visiting. Our sun is moving. It orbits the center of the Milky Way at roughly 500,000 miles per hour, completing one loop every 230 million years. Within that orbit, it also moves relative to the local interstellar medium at about 52,000 miles per hour. This is the speed at which the sun plows through the local interstellar cloud. At that speed, the sun's magnetic bubble is constantly pushing against the local gas. The push creates a wave, not a sharp shock wave, like the boom from a supersonic jet, but a gentler disturbance called a bow wave. Picture a boat on a lake, moving slowly enough that it does not create a breaking wake but fast enough to push water outward on either side. The water piles up slightly in front, curves around the hull, and settles back behind. That is the kind of structure our sun creates in the interstellar medium. The bow wave extends ahead of the heliosphere, possibly for hundreds of astronomical units or more. Within it, the interstellar plasma is compressed and warmed by the sun's passage. The The density ramp Voyager detected just beyond the heliopause is part of this bow wave structure. For a long time, scientists debated whether the Sun created a true bow shock, a sharp discontinuity like the one a supersonic aircraft creates in Earth's atmosphere. Modern measurements suggest it does not. The Sun is moving too slowly, relative to the local sound speed in the interstellar medium, for a sharp shock to form. Instead, we get the gentler bow wave. This distinction matters for how cosmic rays and interstellar plasma interact with the heliosphere. A sharp bow shock would have dramatic consequences, channeling cosmic rays in specific directions and creating strong asymmetries in the heliosphere's shape. A softer bow wave creates more gradual effects. The difference changes predictions for what missions like Voyager should observe, and the observations favor the softer interpretation. The Sun has been making this bow wave for billions of years. Every star of similar mass creates one. The galaxy is filled with these quiet, moving bubbles, each leaving a trail of disturbed plasma behind as it orbits the galactic center. On long timescales, the cumulative effect of all these bubbles contributes to the stirring of the interstellar medium. Stars act like spoons, constantly mixing the galactic soup. Over millions of years, their bow waves and astrosphere interactions redistribute elements, cycle gas through different states, and sculpt the structure of the galaxy itself. Voyager is now in the outer edge of the Sun's bow wave. Every density measurement it makes is part of a profile that, when fully mapped, will tell us how the bow wave looks in detail. Future missions could extend the profile further, but Voyager has already provided the foundation, and the bow wave is not symmetric. The nose, where the Sun meets the incoming interstellar wind head-on, has the strongest compression. The flanks, where Voyager 2 is now flying, have weaker compression. The tail, behind the Sun, has little compression at all, but a long plume of slightly altered material stretching outward. Our solar system leaves a trail, not a visible one, not anything a telescope could ever image directly from Earth, but a trail measurable by plasma instruments, tracked by the distortion of the interstellar medium, visible to any sufficiently sensitive detector. That trail might persist for tens of thousands of years after the Sun has moved on, a ghost of our passage, written in plasma, slowly dissipating as the interstellar medium relaxes back to its undisturbed state. Voyager is the only machine that has ever sampled such a trail. From its own star, if NASA launched a modern interstellar probe tomorrow, it could do things Voyager never could. Modern instruments are vastly more sensitive than the ones built in the 1970s. A contemporary plasma sensor could measure densities, temperatures, and velocities at far greater precision. A modern dust detector could capture individual interstellar grains and analyze their composition. A modern magnetometer could map the interstellar magnetic field in 3 dimensions, not just along a single trajectory. Most importantly, a modern probe could carry its own power system for far longer than Voyager's. Next-generation radioisotope power supplies could keep instruments running for a century or more. A mission launched in 2030 could still be returning data in 2130, long after everyone alive today has died. The science such a probe could do is staggering. It could fly directly through the heliopause at higher speed, measuring the boundary structure in fine detail. It could reach the pristine interstellar medium within decades and characterize it directly. It could sample the local interstellar cloud far from any solar influence, building the first true reference map of a galactic neighborhood. It could also carry optical instruments. A telescope pointed backward at the solar system would reveal our entire stellar home as a single point of light, with Earth and the other planets as pinpricks around it. The parallax angles between the probe's view and Earth's view would be so large that astronomers could measure distances to nearby stars with unprecedented accuracy. Proposals for such missions have names. Interstellar Probe, a concept from the Applied Physics Laboratory at Johns Hopkins. Voyager-like missions studied at JPL. European Space Agency concepts, Chinese concepts. Most remain on paper. The technical challenge is real. To reach 500 astronomical units within 50 years, a spacecraft needs to travel at roughly 10 astronomical units per year, more than twice Voyager's speed. This requires either a much heavier launch or an innovative propulsion method. A solar over-Earth maneuver, where the spacecraft dives close to the Sun and uses a powerful rocket burn at perihelion, is one leading candidate. A direct chemical burn could add the necessary velocity to achieve interstellar speeds. Another possibility is a nuclear electric propulsion system, using a small reactor to power ion thrusters for years or decades. This would provide continuous acceleration, though slower than a rocket burn. Such systems exist in concept but have not been flown. Even more exotic possibilities include laser-driven light sails. A sail illuminated by a powerful ground-based laser could reach significant fractions of light speed, though the engineering challenges are enormous. The Breakthrough Starshot initiative has proposed such a system, aiming for tiny probes that could reach Alpha Centauri within decades. None of these missions are close to flight readiness. The most realistic next step is a larger, slower probe that would reach a few hundred astronomical units within 50 years. Using known technology, even that mission has not been funded. Meanwhile, Voyager keeps going. Every month, the spacecraft remains operational is another month of unique data. Every new whistle, every new hum, every fluctuation in the interstellar medium adds to a record that no other mission has matched. When Voyager finally falls silent, that record ends, and we enter a period where no spacecraft is in the interstellar medium. How long that period lasts depends entirely on what humanity decides to do next. There could be a gap of decades. There could be a gap of centuries. There could be a next-generation probe flying alongside Voyager within 10 years if priorities shift. The choice is political, not technological. For now, the bunny ear antennas keep listening. Right now, as you listen to this, Voyager 1 is transmitting. Its signal is faint, incredibly faint. By the time a radio wave from the spacecraft reaches Earth, it has spread out across so much space that the power detected by our largest antennas is measured in attawatts. That is 10 to the power of minus 18 watts. A tiny fraction of the power it takes to run a light bulb, spread across an entire antenna dish. Only 3 antennas on Earth can hear it. All belong to NASA's Deep Space Network, which maintains stations in California, Spain, and Australia. The station in Australia, at Canberra, is the only one with a clear line of sight to Voyager's current position in the southern sky. Every week or so, the Deep Space Network schedules a listening session. The antenna turns toward Voyager. The signal comes in, barely above the background noise of the universe. Engineers extract the data, carefully, byte by byte. The data rate is absurdly slow, about 160 bits per second. For comparison, a modern home internet connection is roughly 1,000,000 times faster. A full day of Voyager data amounts to less than 1 megabyte. That entire day of transmission would not even cover the size of a single high-resolution photo taken with a smartphone. But every byte matters. Every byte is a measurement from interstellar space. The spacecraft's power is slowly declining. Its plutonium-238 fuel source produces less heat each year, and the heat is what generates electricity for the instruments. Engineers have been turning off systems one at a time to conserve power. Non-essential heaters have been shut down, allowing portions of the spacecraft to freeze to temperatures colder than they were ever tested for. Miraculously, the instruments keep working. Each year, NASA evaluates which instruments to keep running. Each year, hard choices get made. The plasma wave subsystem, the bunny ears, is one of the highest priorities. Its data is unique and irreplaceable. The magnetometer is another. The cosmic ray subsystem continues. Others have been shut down to preserve power for the essentials. Current estimates suggest Voyager 1 will be able to keep at least one instrument running until roughly 2028 or 2029, maybe longer if engineers keep finding ways to extend its life. Eventually, though, the power will fall below the threshold needed to transmit a signal. The spacecraft will still be intact, still drifting outward, but it will go silent. When that happens, the era of direct interstellar science will pause. We will continue receiving data from orbital observatories, computer models, and indirect measurements. But no spacecraft will be reporting from the medium itself, not until a new mission is launched and completes its outbound journey. Voyager 2 will follow a similar decline. Its instruments are being shut down in a similar sequence. Some estimates put its final transmission in the early 2030s. Until then, both spacecraft continue their work. Every dataset returned extends the record of humanity's first direct contact with interstellar space. Every bit transmitted is a tiny signal reaching across 15 billion miles of vacuum, landing on a radio dish in Australia, adding another line to a story that began in 1977. The engineers who built Voyager are mostly retired now. Some have passed away. The new generation of mission controllers has inherited the spacecraft from their predecessors. They talk about it with a kind of reverence. A machine older than most of them, still working, still reporting from the far edge of the solar system. One day, they will send the last command. One day, they will receive the last signal. One day, they will close the logbook. But not yet. Take a single light year. The distance light travels in 1 year, moving at 186,000 miles per second. That is about 5.9 trillion miles. Now, imagine a cylinder, 1 meter wide, stretching across that entire distance. A thin tube, 1 yard across, extending for almost 6 trillion miles. At the density Voyager has measured in the local interstellar cloud, how much matter is inside that tube? The math works out to something surprising. Enough hydrogen to fill a small swimming pool. If you could compress all the atoms inside a light-year-long, meter-wide cylinder into a container at atmospheric pressure, it would fit inside a room. Not a large room. A closet, maybe. That sounds like almost nothing. But remember, a light year is a small distance by galactic standards. Our own galaxy, the Milky Way, is roughly 100,000 light-years across. Multiply out across these scales, and the total mass of the interstellar medium in our galaxy alone is enormous, somewhere around 10 billion times the mass of our Sun. The galaxy is mostly space, but the space is full of something, and the something adds up. This is one of the hardest concepts in all of astronomy. Density so low that it seems like vacuum, multiplied by volume so vast that the total is still astronomical. Our intuition fails. We think of empty and full as binary categories. But in space, everything is somewhere in between. Here is another way to picture it. If you could scoop up every atom between here and the nearest star, Proxima Centauri, and pile them together, you would have enough material for a single large asteroid. Not a planet, not a moon, an asteroid. Across 25 trillion miles of empty space, there is only that much matter. Yet the matter is there. It affects starlight. It carries magnetic fields. It propagates shock waves. It shields planets from cosmic rays. It forms new stars when it gets compressed enough. Over long timescales, it dominates the evolution of the galaxy. Voyager is sampling this material directly. Every cubic mile the spacecraft sweeps through contains, on average, a tiny handful of atoms. Over the course of its flight, Voyager has encountered an enormous number of atoms in absolute terms. But at any given moment, the spacecraft is effectively alone. This absolute low density is why we did not detect the interstellar medium directly for most of history. There was not enough of it to see with old instruments. You needed extremely sensitive detectors, spread across decades, to find the signal. Modern astronomers can now routinely measure the interstellar medium in huge detail. Ultraviolet spectrographs track atoms by their absorption fingerprints. Radio telescopes map cold hydrogen across the galaxy. Infrared observatories image dust in star-forming regions. But all of those techniques are indirect. They measure signals from the interstellar medium at a distance. Voyager is the only spacecraft that has directly touched it. And the more Voyager samples, the more researchers realize how dynamic the medium really is. It is not a static backdrop. It is an active, flowing, churning fluid that carries the history of the galaxy within it. Every atom has a story. Every density variation reflects some past event. Every magnetic field line traces a flow that has been going on for millions of years. The galaxy is not mostly empty. It is mostly diffuse. That is a better word. Empty implies nothing is there. Diffuse implies something is there, but spread thin across vast distances. The interstellar medium is diffuse. The space between stars is diffuse. Our own local neighborhood is diffuse. And diffuse matter, spread across billions of light years, adds up to most of the universe. Stars form from interstellar matter, specifically from dense, cold, molecular clouds, where gas collapses under gravity. Every star you can see, every star in the galaxy, started as a patch of interstellar medium that happened to get dense enough to pull itself together. For this process to work, theorists need accurate models of how the interstellar medium behaves, how it flows, how it mixes, how it transitions from diffuse, warm gas into cold, dense clumps, how magnetic fields and turbulence affect the process, how supernovae trigger new star formation in the compressed shells around their blasts. Voyager's measurements affect every part of this picture by showing that the local medium is more structured, more turbulent, and more magnetized than simple models assumed. Voyager has forced theorists to refine their simulations. New star formation models now incorporate the kind of Au-scale turbulence the spacecraft detected. They account for the persistent plasma waves that signal ongoing energy flow through the medium. They include the kind of layered density structures the spacecraft has mapped. One specific area of impact involves the transition from diffuse to dense. How does a large region of warm, thin, interstellar gas become a cold, dense, molecular cloud capable of forming stars? The process takes tens of millions of years, involves shocks from supernovae, and requires specific conditions of pressure and temperature. Voyager's data on local turbulence and density fluctuations helps constrain how fast this transition can proceed. If the turbulence is too strong, gas cannot collapse. If it is too weak, every region would be collapsing and the galaxy would be a star-forming frenzy. The observed rate of star formation in the galaxy is consistent with the turbulence levels Voyager has measured, at least in order of magnitude terms. Another impact involves cosmic ray feedback. Cosmic rays ionize interstellar gas, which affects its temperature and magnetic behavior. Voyager's measurements of the galactic cosmic ray flux in the local environment allow researchers to better model this feedback effect. Higher cosmic ray fluxes tend to suppress the formation of very small, dense clumps, slightly inhibiting star formation. Lower fluxes allow more clumps to form. The balance depends on the specific cosmic ray spectrum, which Voyager has measured in detail for the first time. This matters for understanding why the galaxy forms stars at roughly a few solar masses per year. Models must reproduce that rate, and they can only do so if they include the right physics of the interstellar medium. Voyager has provided ground truth data that constrains those models. On larger scales, the discovery that our local bubble is a cavity carved by supernovae is part of a broader realization. Most star-forming regions in the galaxy are triggered, directly or indirectly, by the shockwaves of previous supernovae. Stars are born in the aftermath of other stars dying. The galactic ecosystem cycles matter through stages of diffuse gas, dense clouds, stellar formation, stellar death, and back to diffuse gas. Voyager samples one small corner of this cycle, but the sampling is detailed enough to inform the whole picture. Every measurement ties into theories about star formation rates, galactic chemical evolution, and the long-term fate of the Milky Way. The galaxy is a self-renewing engine. Dead stars feed new stars. The interstellar medium is the conduit through which that feeding happens. And Voyager, for the first time in history, is giving us in situ data about what that conduit actually looks like. Our models are better because of the spacecraft. Our understanding of star formation is more realistic. Our predictions for how the galaxy will evolve over the next billion years are more accurate, all from two machines launched before the Rubik's Cube went on sale. At the start of this journey, the idea was simple. Space is empty. That idea is gone. Voyager has shown us that the space between stars is layered, pressurized, humming, turbulent, magnetized, and full of matter. Diffuse matter, yes, but matter, enough of it to shape the evolution of galaxies, influence the development of life, and rewrite the maps of our local neighborhood. Our solar system is not floating in a vacuum. It is embedded in a cloud of ancient stellar debris, carved from the galaxy by supernovae 14 million years ago. Our sun is plowing through this cloud at 52,000 miles per hour, compressing the gas in front of it into a pile-up zone. dragging magnetic fields into a draped layer and generating shock waves that echo outward for years after every solar storm. Our protective bubble, the heliosphere, is not a sphere. It is probably a croissant, or a teardrop, or something shaped like neither, with foaming magnetic bubbles along its edges and stagnation regions where the solar wind slows to zero. Beyond the bubble, the galactic environment is denser than we ever realized, 20 to 30 times denser than the space inside the heliopause, full of cosmic rays accelerated by distant dying stars. Stirred by turbulence on scales we can now measure directly, humming continuously at frequencies the bunny ear antennas can hear. All of this was invisible to humanity for most of our existence. Now it is mapped. Now it is recorded. Now 2 small spacecraft, drifting away from Earth at a combined speed of over 100,000 miles per hour, are giving us our first real look at what was out there the whole time. The word empty was always a simplification, a way to make the universe feel manageable, a way to draw clean diagrams in textbooks. The real universe, the one Voyager is flying through right now, is messier and richer and stranger than we allowed ourselves to imagine. And the messier picture is better. It is more accurate. It is more honest. The interstellar medium is alive with structure. It carries the history of every star that ever died nearby. It conducts signals from one side of the galaxy to the other, not as sound but as plasma oscillations that cross light years. It shields planets and exposes them. It seeds new stars and new worlds. It forms the connective tissue of the Milky Way itself. Voyager has shown us this tissue up close. The spacecraft is now at the furthest edge of human reach, and it will keep going long after its batteries die. In 10,000 years, it will still be drifting through the local interstellar cloud. In 100,000, still. In 1,000,000, it will be somewhere in the galaxy we cannot predict, carrying the same gold record of Earth sounds, the same engraved map pointing back to our sun. Whoever or whatever finds it will find a machine that reported, for a brief window, on the medium it now drifts through. A machine that changed its civilization's understanding of what lies between the stars. The answer was not nothing. It was never nothing. The answer was everything in between, and we finally have ears to hear it.